This video, as you can see, is all about the use of tables to calculate probabilities from a binomial distribution. And the first question is, why do we need to use tables? So here's an example. Suppose we've got a distribution where n is 15 and the probability of success is 0.35. And maybe we want to find the probability that x is less than or equal to 3. Now clearly the probability that x is less than or equal to 3 is the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. So we need to calculate all these probabilities separately. So here is the full working for this. So probability that x is less than or equal to 3 is 0 plus 1 plus 2 plus 3. The probability that x equals 0 is given by that formula, x equals 1 that formula, x equals 2 that formula, x equals 3 that formula. And then you work out each bit separately and you get the answer of 0.3467. So it's not especially hard, but it's obviously time consuming. And we may want to find out numbers much bigger than that. X is less than or equal to 10. We'd have 10 or 11 things to work out. So in this case, we need to find a shorter way of doing this. But there's nothing wrong with this method, it's just that it's very long-winded. And the tables will save us lots of time. So here is the relevant page from the formula tables. Obviously we need to make sure we're using the right page. So the original question was here, x is a binomial distribution, n is 12, and the probability of success is 0.35. So here we've got 12, and along the top we've got the probability is 0.35. The next section is 15. So if we have a situation where we've got 13 or 14 for n, then we can't use the tables. But okay, we can use it for 12, we could use it for 15, we'll do that later. Notice that the numbers along the top go up in multiples of 0.05 up to 0.5, so we can use 0.35 at this point here. If the probability of success was 0.34, then we couldn't use the tables. But in this situation we've got n is 12, 0.35, so it's this column here. We want the probability that x is less than or equal to 3. It's here. If we read across from 3, we can see that it's 0.3467. Which is the same result as we got before. And clearly that is much quicker, that's a much quicker way of doing it. Here's the second example. In this case we've got another binomial distribution, 15 trials, the probability of success is 0.3. What's the probability that we get 5 or more successes? So this is different because we're finding a number greater than or equal to 5. Previously we had less than or equal to. The tables will give us the figures which are less than or equal to a particular number. So let's consider all the possible numbers that we could get. We've got from 0 up to 15. We want the probability that x is greater than or equal to 5. So that's all those numbers there. So remember that these numbers 0 to 15, they exhaust every possibility. So either we're going to get greater than or equal to 5, or we're going to get less than or equal to 4. So this is quite a fundamental point. So important, I'm going to say it again. We're after the probability that x is greater than or equal to 5, so that's all these numbers here. So either all the numbers are greater than, so the numbers are greater than or equal to 5, or they're less than or equal to 4. So from that we can say that the probability that x is greater than or equal to 5 is 1 minus the probability that x is less than or equal to 4. So here we are, we've got a binomial distribution where we've got 15 trials, the probability of success is 0.3. The probability that we get greater than or equal to 5 successes is 1 minus the probability we get smaller than or equal to 4. So if we go to the right part of the tables, we've got 15. So we've got 15 here. We're looking at 0.3 and we're looking at 4. So we've got 0.3 here, we've got 4 here, so we've got 0.5155. So by reading across from 4 down from 0.3, we get 1 minus 0.5155, which is 1 minus 0.5155, squeeze it in here, which is 0.4845. And that's obviously only correct to 4 decimal places. Here's a third example. We've got a binomial distribution, 15 trials, the probability of success is 0.45. What's the probability that the number of successes is between 6 and 10? It could equal 6, but it couldn't equal 10. So we need to have a look at this row of numbers again. We want x to be between 6 and 10. It can equal 6, but it can't equal 10. So in other words, we want 6, 7, 8 or 9. So therefore, these numbers are all the numbers up to and including 9, minus all the numbers up to and including 5. So you just need to make sure you're happy with that. So between 6 and 10 is 6, 7, 8 and 9. So we work out the probability that x is less than or equal to 9, which is all of those, and they have to take away less than or equal to 5. So what we get is the probability that x is between 6 and 10 is the probability that x is less than or equal to 9 minus the probability that x is less than or equal to 5. Make sure you understand why that's a 5 there and not a 6, because we're taking those numbers away. So let's use the tables to find out this answer. Remember, x is a binomial distribution, 15, 0.45. Here's 15, here's 0.45. We want less than or equal to 9 to start off with, so we go down to 9 and we get 0.9231. There it is, 0.9231. And then we need to take away the probability that x is less than or equal to 5. So again we're on 15, 1.45. Need to take away the probability less than or equal to 5. That's 0.2608. So 5. And when we do that calculation, we get 0.6623. Here's another example. This time we've got the binomial distribution with 15 trials. The probability of success is 0.25. What's the probability that x equals 7? There's two ways of doing this. One way is simply to say this equals 15c7, 0.25 to the power 7, 0.75 to the power 8. And that works out to be 0.0393. Personally, I think this is the best way of doing it, but you can use the tables to do this. So let's think about what numbers we've got. What we want is the probability that x equals 7 exactly. So the probability that x equals 7 is here, that's 7. So what we need to do is to find out the probability that x is less than or equal to 7 and take away the probability that x is less than or equal to 6. So we've got the binomial distribution with 15 trials and 0.25. So 15 is here, 0.25 is here. So we need to find the probability that x is less than or equal to 7. For 0.25 we get 0.9827. There it is. So that's 0.9827. Then we have to take away when the probability x is less than or equal to 6, which is there, 0.9434. So 0.25, so it's 6, so it's minus 0.9434, which is 0.0393, which is what we got before. So although personally I don't think this is the quickest way of doing it, some people prefer doing that. So when it's exactly equal to a number, you've actually got two possible ways of doing it, going back to the original way of working out binomial probabilities or using the tables. Okay, one more example. Okay, this is a harder example. Here we've got a binomial distribution with 15 trials and the probability of success is 0.8. What's the probability that the number of successes is a number that's smaller than or equal to 10? So here's the section for 15, but you will notice that the probabilities stop at 0.5. So we can't read this off from the tables. But luckily there is a way of doing this, and if we think of x is the number of successes, think about how many failures there are. Let's call that y. Y is the number of failures. And I think drawing a table out like this is quite helpful. So we've got here x is the number of successes. So for example, if there's 3 successes, well, there must be 12 failures. If there's 10 successes, there must be 5 failures. If there's 13 successes, there must be 2 failures. I think setting it out like this is quite important. I've had to squash it in on this, but you could set it out with a little bit more clarity. So what we want is x to be smaller than or equal to 10. So what we're looking for is these numbers here. So we want x to be less than or equal to 10. In other words, we want y to be greater than or equal to 5. Just to give you a bit of time to think about that, we want the number of successes to be smaller than 10, so we want the number of failures to be greater than or equal to 5. So what we're after is the probability that y is greater than or equal to 5. Now, as before, that's 1 minus the probability that y is less than or equal to 4. But what is the distribution of y? We know that x is a binomial distribution, 15 trials, probability of success is 0.8. So for y is part of the binomial distribution, 15, and the probability now is obviously 0.2. So from here we can see we've got 0.2, we've got 15, we want y to be less than or equal to 4, so that works out to be 0.8358. So back to here, I'm running out of room, so I can say that this probability here, so I get 1 minus 0.8358, which is 0.1642. Obviously you wouldn't set your work out so terribly. This bit really I should have put up there. But anyway, that completes this example of how to deal with a situation where the probability you've got is greater than 0.5.